Okay, so I will continue. So I remind what we are discussing, that if X is complex algebraic variety, so we defined category D of X, we fix some K some field, coefficient field. D of X, which is just bounded derived category of sheaves on analytic space X is coefficients K. And what we discussed, this is triangulated category, and what we discussed is there is a perverse T structure. And heart of the structure is category of perverse sheaves on X, which is an abelian category, which I try to explain that this is a real character in the story. And we have seen that just existence of this thing allows to, for instance, to make some constructions which otherwise are difficult to do. Now the idea is that we would like to use some results of algebraic geometry, and it turns out that somehow in algebraic geometry it has two stages. There are some standard results. So algebraic geometry, it is somehow non-trivial. So there is algebraic geometry, so there are results like Chevalier theorem, non-singular things, and Riemann-Roch, so on. So this is all level 1. And there are level 2, which I would write it weight filtration. So the idea is that this thing is not really done. So it's done in some cases and so on. So let me give you some. So the idea here is that we have algebraic variety. Then the claim is that in its cosmology there is some kind of filtration which you don't a priori see.
When you say cosmologies, you mean not classical?
Some cosmology, okay. For instance, cosmologies of complex algebraic varieties. There is some structure which you don't see directly, and all morphisms which you even don't know about have to preserve this structure. So hence you have some very severe restrictions on possible morphisms. So let me give you examples of such phenomenon. First example is Hodge decomposition. Hodge decomposition. That's, I think, was the first place where it was discovered. So what you have is that, so suppose this X is projective example, smooth variety over C. Then you have exact sequence. You have complex of sheaves omega naught, omega 1, omega 2, omega n 0, where these are sheaves of holomorphic differential forms. Now, in analytic topology, these sheaves give you resolution of constant sheaf C. Now we can, from this you can immediately write down some spectral sequence you define HPQ of x by definition is equal HP of x with coefficients in omega in sheaf omega q. So you can consider analytic homology or algebraic, it is the same. And then from this resolution you can immediately see that there exists spectral sequence that starts with HPQ and tends to cohomology, usual cohomology of x with coefficients C. And now, so this is easy fact from Sheaves theory, just immediately see it. If you do it, for instance, in analytic topology, then it's just.
So omega q is the
sheaf of Q forms.
But analytic q forms are.
So the idea is you can do it in analytic topology, you can do it in algebraic topology, according.
Is normal.
Hmm?
In the smooth.
No. I am not considering smooth. So this is all. So, but the idea is that by Gaga, in analytic topology and algebraic topology, you get the same answer. So it doesn't really matter.
N is P plus Q.
So when you have spectral sequence, so it, okay, N will be equal to P plus Q. So, and now non-trivial fact is that this spectral sequence effect degenerates. All the differentials are equal to 0. This is Hodge decomposition.
And this is true only for projective smooth variety, it's not true in general.
So what do you mean in general?
So this spectral sequence exists for.
You need
What do you need?
if it's caramel, go.
No, but for algebraic variety, if it's not.
No.
Projective, we still can write everything down. And if it's not smooth.
So first of all, the idea is that first of all, then this matter whether it is analytic or algebraic will be different, and then you can write so what.
So it will degenerate the spectral sequence?
No, of course not. No, nothing.
Projective smooth or complete smooth variety.
But okay, I don't know. Okay, probably it's true for complete, but I don't know. So this is one example. So another example is, for instance, Hard-Lefschetz theorem. So what is Hard-Lefschetz theorem? Again, for X is smooth projective variety. Projective. We embed it into Pn. And then we get class omega in H2 of Pn and hence in H2 of X. You can consider it class omega in H2 of X. And you consider cohomology of X and consider operation multiplication by omega. So this operation of degree plus 2. So the claim is that you can consider also operator H, which is degree minus m. X is smooth, projective.
Of Pn?
Yes. Smooth projective of dimension m. Consider operator H equal degree minus m. So then the claim is that there exists an operator lambda of degree minus 2.
H is element.
H is operator of degree 0, which is multiplication by degree minus m.
So could you repeat it? I did not understand.
So on Hi, it is multiplied by I minus m.
Just physically, you say what the eigenvalues are.
Yes, well, it's just essentially the same gradient, but shifted by m. So then the claim is that there exists an operator lambda of degree -2 such that this forms in cohomologies of X. There exists operator lambda of degree -2 such that they form SL2 triple. Standard commutator, so commutator lambda and omega will be equal to H.
Could you repeat all of this, because I
Yes.
missed the part where you define what's an operator here?
So we consider cohomology of X.
Okay.
It is graded thing. So we consider here the following operator. Operator H is essentially grading shifted by M. So on HI, so H is restricted on HI is equal I minus M times identity. So then the claim is that there exists operator of degree -2 such that they form SL2 triple. When things form SL2 triple, it's a very strong condition for it. And since here the range of H is small, bounded, so it is extremely strong condition.
You identify omega with the operator cup
Hmm?
product by omega?
What?
By, omega, you mean actually the cup product by omega?
Yes, yes, omega is multiplication by omega. Consider, yes. So this is very strong result. Again, it's difficult to get it algebraically. So this was proven again the same way as Hodge decomposition by using differential forms. And
The claim is if there exists an omega.
no, omega is no. Omega is given.
We start with
This
some
starts
omega, and then you
Omega,
find the H,
or-
and then there
Not
exists
some, not some omega. This omega which corresponds to what's called hyperplane section.
Hyperplane section.
Hmm?
Where do we have hyperplanes?
What?
I'm confused as to where do we start.
We consider some algebraic projective algebraic variety
Yes.
of dimension m and Pn.
Yes.
So then class, two-dimensional class in Pn. Homology of Pn is polynomials of omega. So I stick this to cohomology of X and consider multiplication by this element. The claim is that it canonically embeds into SL2 triple. And this gives you, so you can read many different incarnations of Hartley-Lefschetz theorem, but that's correct way to say it. So from the fact that it's SL2 triple, you can immediately deduce that it's isomorphic to something, primitive elements, and so on and so on. That's tautology. Okay, so from here, for instance, next thing which was proven by several people, Delinian, the following thing. Suppose you have pi xy proper smooth morphism of algebraic varieties. Then we can write a spectral sequence from HP of fibers of fiber of pi minus 1 of y HQ, and here you consider HP, which converges to cohomology of P plus Q of X. No, this is standard spectral sequence. And the claim is that this sequence in this situation always degenerates.
So inside the HP, is there a hint what sheaf we are taking?
No, but I didn't understand. You have, this is fibration. For fibration, you write standard spectral sequence. So for topological spaces, there is a spectral sequence, okay? Now the claim is that if this situation is algebraic and this projective morphisms and projective smooth fibers, then this sequence degenerates. All differentials are equal to 0. And hence, the cohomology of X is essentially more or less equal to the product of cohomologies of Y and cohomologies of fiber. Again, so these are just examples where you can see that.
So HQ is the phi minus 1 is the sheaf on Y.
What?
The thing in the bracket is
The hint for that sheaf. It's the phi minus of that sheaf.
No, I consider, okay, so this is topologically, this is just fibration. So if you have a fibration, then you have spectral sequence which relates, you consider cohomology of fiber, consider as a sheaf on Y, consider cohomology of Y with coefficient on this C. So you get some group which depends on two variables, P and Q. And from this C, you put spectral sequence, compute something, and eventually you'll get cohomology of the whole space. This is standard. What is not standard is that in this case, this spectral sequence degenerates. All differentials are equal to 0.
And that means that topologically it's actually a product?
No, of course not. Why?
But somehow the homologous looks as
Yes,
a product.
homologies look like it's a product. And again, the proof essentially it reduces Hodge decomposition. So essentially, this differential, they act in such a way that which is forbidden. There is this weight filtration. It's forbidden, so they have to be equal to 0. So this is just some examples of this situation. And so I think that probably Grothendieck was first who realized this very general phenomenon, and he published a paper which is called Standard Conjectures, where he listed some conjectures which should be true for any.
And those
For example,
will imply easily all those theorems.
What?
And those conjectures will imply all those theorems kind of easily.
Yes. Okay, so I don't know. He lists up the relation between them. So let me just formulate, since we're here, I can formulate one of these conjectures. Namely, we had this element lambda. This is morphism from cohomology of X to cohomology of X with degree -2. No, it's easy to see that any such morphism is given by cohomology class lives in cohomology of X cross X. It's easy to see that any cohomology, any morphism in cohomology can be described. No, yes, it's just that any matrix can be described as element in vita and the star. That's all.
And can be described.
Yes, so one of standard conjectures is that this lambda has algebraic nature. That in fact there exists some kind of algebraic cycle which generates this lambda. So this is not clear at all from the proof. The proof is purely analytic, something is positive, some whatever. So this is one of standard conjectures.
What is one of standard conjectures?
That this lambda is algebraic, generated by some algebraic cycles. It's even dimensional cohomology class, so it can be generated by algebraic cycle, and the claim is it should be algebraic. Okay, so
Can you say one word about the
Yeah.
weight filtration? You mentioned the weight filtration and
Okay, so I
difficult for me to connect the dots to what you were.
so no. So for instance, the proof of this theorem about the degeneration spectral sequence is in terms of some wave filtration, but I will talk about this later. Okay, and so so now to formulate this conjecture, so Grothendieck formulates this conjecture for other fields, namely, and that's what we'll discuss later today, that if X is algebraic variety over some algebraically closed field K, then we'll discuss today that you can define something like Hn of X, some analog of this for some fields K, which in complex case will be just usual cohomologies. And you can formulate all these conjectures in this case.
Usual is analytic. Usual means analytic. When you say
Yes. Okay. Yes, usual means analytic. Okay, I will discuss it in several minutes.
Now X is not necessarily projective or complete, or just algebraic variety.
So we'll discuss this in a moment. So you can formulate all these conjectures, not all, sorry, not Hodge conjecture, but for instance, the degeneration of spectral sequence and hard Lefschetz. You can formulate for these cohomologies. So this is also part of standard conjectures. Okay, and now for the case of finite fields, Deligne proved these conjectures, almost all of them, by using, okay, so that's what I will discuss later. And now, as a result, we have the following situations. So these conjectures give some very strong tool of proving some things. For instance, strong Lefschetz theorem and so on can be applied. And we'll see later that it actually allows to do a lot of computations, which are otherwise possible to do. No? So some indication is that this, if you have spectral sequence, then it's very nice, but if you don't know differentials, then it's not that easy to tell anything. But if you know the differentials are equal to 0, it gives you more or less the answer. So similar thing here. And now it turns out that perverse sheaves are very much related to this, namely, namely the idea is that so in case of finite fields, we can, using this Deligne's approach, we can prove many results, can do many computations. And then there are some tools how to reduce problems in characteristic zero, for instance, our complex numbers, to problems in our finite field. So as a result, for instance, we can tell a lot, and it turns out that so the idea is that since these perverse sheaves are natural objects, then it's natural to expect that they are well adapted with respect to this mysterious filtration, weight filtration. And it turns out that over finite fields, it's just literally true. It can be proven. Over arbitrary fields, since we don't quite know what is this filtration, we only, so to say, guessing. It's not proven. So as a result, very many, you can prove many results about perverse sheaves and do many computations in the following way. You consider some perverse sheaves over complex numbers. Then you go to the similar picture over finite field. of finite field, you can use these Deline's results, and you prove some theorems, and from this you deduce the theorems for complex numbers. So there are many results which you can obtain in this way. And so there are, so this is in fact standard way to get some stronger results about perverse sheaves, like for instance Cauchy-heuristic polynomials we will discuss, some equivariant cohomologies and so on. We'll discuss this later. But somehow it requires this kind of this requiring studying what is going on over finite field. And that's what I want to explain. But just I want to say that it turns out that most of these results you can somehow, usually you can do purely over complex numbers, for example. If you use one theorem, which is for which you should go to. So I will formulate the theorem which, for the proof of which theorem, the only known proof is, okay, maybe not the only, okay, this I don't know. So you should go to positive characteristic, but it can be formulated without positive characteristic, and the claim is that many of strong results about perverse sheaves you can reduce without going to positive characteristic, reduce to this one statement. So let me formulate this. It's called decomposition theorem. So consider x as before and consider dx. Consider some object f dx. So we say that f is semi-simple if f is isomorphic to direct sum of Li shifted by Ni, where Li are irreducible perverse sheaves.
Dx is a derived category of
Yes. That's what we had before. So it's not necessarily perverse sheaf, but it is somehow sum of irreducible perverse sheaves and maybe some, maybe shifted. Okay, so let's formulate the first quasi-theorem. Suppose I have morphism pi x to y. What I want to show is that sometimes it maps semi-simple elements into semi-simple. So first is that if pi is projective, in fact it's proper also, okay, projective, then pi star maps semi-simple to semi-simple. And second, if pi is smooth, then pi star and pi shriek, in this case pi shriek is equal to pi star, map semi-simple into semi-simple. Okay, second is just obvious, it's not interesting. And first is important. So what essentially what it tells you that semi-simple go to semi-simple, it means that just irreducible perverse sheaf will go to semi-simple. That's now it's not okay. I know how to prove this theorem. I don't know how to prove this theorem for any reducible sheaf, but I know how to prove it for sheaf of geometric origin. For example, I see a sheaf on some x. So the idea is that I prefer to think about it in this way. So maybe now, by now, maybe it's proven for. I don't really know. I haven't followed this. Maybe it's proven in more general situation. But the idea is that in all applications which I know, you can just decide that it's true for all things. And then when you do applications, then everything which you need for it will come from geometric origins. Okay, so once more, this theorem is good because it often allows to avoid going to something in positive characteristic. You have a theorem and you prove it by using, you have some statement which you want to prove, and using this decomposition theorem you can prove it. That again, somehow there are no, the claim is that there are no relation between, when you consider direct image here, then things don't glue together. So, okay, so, but I should say that nevertheless that it's usually possible, but it's for me going to positive characteristic is preferable because somehow things become a little clear when you go there. But once more, but I want to say that all this is because we don't have this, so say, nobody proved Grothendieck's standard conjectures. If you would prove them, then you wouldn't need to go anywhere.
So we should follow from the Bernstein conjectures?
Yes, of course. No. So when, no, okay, so essentially, no, the idea is that, okay, we'll discuss it. So when Grothendieck formulated it, there were no perverse sheaves or anything like this. So he formulated about cohomologies of varieties. But essentially you can say, okay, so maybe there should be some slight extension of Grothendieck's things. Okay, so just what I wanted to say.
Maybe the weights explain why this is true.
What? Why what is
so
true?
You mentioned the weight filtration, and weight filtration, if I understand correctly, is a philosophical reason why this is true.
So why this is true? No, so the proof.
It's true because each of
So the proof goes like this. So first you prove this theorem for over finite field. Over finite field you prove that any reducible perverse sheaf has, we'll discuss it, has definite length, a definite weight. Then its direct image with respect to projective morphism also has the same weight. Then you prove that if you have any element of the F category which is pure weight, then it is semi-simple. And then you say that if it's true for all finite fields, then it's automatically true for complex numbers because you can approximate complex numbers by finite fields.
But not for all sheaves, but only for sheaves.
Yes, but only in this proof only works for sheaves which you can describe. So complex numbers you can describe by finite number of parameters. Then you can reduce them modulo p, and you can see them when you reduce. Okay, so
not like all the smooth sheaves you describe a representation of pi1. This you can do.
no, pi1. It's not clear.
So even smooth, even local systems,
No.
there are some local systems which are bad.
Yes. No, for example, okay, so there are some local systems.
There is an
So-
alpha there in this.
No, so what's local system? Let's consider the following nice space. Pi1 minus 3 points.
P1.
P1 minus
Pi1 is a free.
P1 minus 3 points. Pi1 is free group of two generators. So it's very easy to construct some reusable representation of this group. You get some local system. You cannot tell anything about this local system. It's not completely not algebraic object.
Okay, and these are some nice descriptions of what are the algebraic local systems? In this case, what representations? A pair of matrices. When the pair of matrices is
No, so there are, I think, necessary conditions. So necessary conditions, for instance, that if you go around each of these things, you get some quasi-important matrix.
Right.
There's some power of it is unipotent. So the eigenvalues are roots of 1.
So even with punctured plane, like
Hmm?
if I have plane without 1 point,
Yes.
so you say not any monodromy is okay? Only with
Yes.
unity, so okay.
Yes. If you want to get it, so do you want to get monodromy which is pi?
Maybe not, but 2, okay. No, maybe not 5, maybe.
No, two is.
Get any number.
two-
That's what
two-
I said. So, yeah. Too many
No,
numbers.
Two is-
but I can't get any elatic number. Or
What do you mean, logic number? Vector
okay.
complex
Yeah, I
numbers.
know, but, then when you do it over FP, I can do.
No, you can.
So in the break,
Okay, so
should be also-
you can. Okay, so I don't see what we are discussing. Okay, so now let's change gears and try to. I will try to describe what is this cohomologous finite field and so on. So I want to tell the story. So probably most of you already heard the story, but we would like to repeat it. So it was in 1947, I think, Wade conjectures.
48 is partner.
Hmm?
I cannot forget the day.
So it's 1947 or 1949, I don't remember one of these two. So he had the following paper where he describes the following conjectures. So if you have X is algebraic variety over C, you can consider the following nice invariant cohomologies of X analytic with coefficients in some field or in coefficient Z. If you have morphism of such varieties, then you have corresponding morphism cohomologies of Y, cohomologies of X. And he said that, and gave some examples, that he conjectures that, in fact, if you have variety over any algebraically closed field, so let omega be an algebraically closed field. And X is algebraic variety of omega. So then there is some general ideology in algebraic geometry that such variety X over omega is similar in properties to some algebraic variety over C. The properties of algebraic varieties over algebraically closed fields are very much similar to properties of algebraic varieties over C. It's not completely correct, because there are some phenomena which are present in positive characteristic, not present in characteristic 0, for instance, some completely inseparable maps, so on. But nevertheless, many properties are very similar. And he said that probably this means that such varieties, so if given x over omega, we can attach some hi of x is coefficient in some field. And to given morphism y, we can attach morphism pi star hi of y into hi of x. And now why he was interested in this? His idea was the following. His idea was to use this thing for applications to number theory. Namely, he said that suppose let X be an algebraic variety over Q over FQ. No, probably projective and smooth. Smooth, just two. No, not X, excuse me, let's Z. So then what you can do, you can consider X, which is corresponding variety with lift of S of Z to omega, which is FQ bar. Consider the same algebraic variety over FQ bar, or it extends scalars. Then this X comes with additional structure. You have morphism Frobenius from X to X, Frobenius Q, which on the level of coordinates is that you just consider Q's power. You have morphism on the level of coordinates, just you consider any coordinate in Q's power, and this is, if you had point in X, then you'll end up again at point in X. So it's just some explicit morphism. And fixed points of this Frobenius are just points of our algebraic variety over FQ. So you can ask the following question: how many points does this variety has over FQ? And the answer is that this collection of points is just fixed points of some endomorphism of your variety. Now, for fixed points of endomorphism, now we should remember, so this we are working over algebraically closed field, so hence the situation should be similar to complex numbers. And here quotes Lefschetz formula. That if you have, in fact, it is for real varieties, but you can also consider complex varieties. You have complex algebraic variety, projective, smooth, and you have some endomorphism of it. Then the number of fixed points of gamma is equal trace of gamma in cohomologies, which is sum minus 1 to the I, trace of gamma restricted to hi of x. So this is definitely true for complex algebraic varieties. And he said that something like this should be true of algebraic closure of FQ. And this would allow us to get some number theoretic results. So, for example, let's see immediately what it would give. Let's consider now number of points at x, f, q to the L. Let's consider not one number, but collection of numbers. Then this will be equal to the trace of Frobenius q to the L, which is just Frobenius q to the power L. So it means that we have some space, finite dimensional vector space, K, graded vector space. We have some operator from this space into itself. And then we can recover all this collection of numbers in the following way. Just consider powers of this operator and consider trace. In particular, this operator has finite number of eigenvalues. So trace you can compute as some powers of this, sum of powers of these eigenvalues. So this gives you first quite non-trivial result. So this number of points as function of L is sum of several geometric progressions. So from this conjecture, just immediately follows this. Okay, and in fact here also so this was first part of this conjecture, and the second part of this conjecture was that if x is smooth projective, and lambda is eigenvalue of Frobenius q in hi of x, then lambda, absolute value of lambda is equal q to the L over 2, I over 2, HL, L over 2.
That is not a good choice after you.
Yes?
Doesn't matter.
Okay, maybe.
Okay. People will still have
Okay, let's J. So this was second. So we will discuss this also. So this was okay. So now I want to make some comments which he also made. Namely, all this is very nice, but there is one problem. Namely, over what is the field of coefficients which we want to. First, okay, I will. Okay, so I will describe the problem, and I will describe somehow he hasn't just introduced these conjectures out of nothing. He, in fact, had examples where he could, by hands, define the thing and explain that they have correct shape. But first, there is some problem which somehow I don't understand what is the meaning of this problem. Namely, the claim is that counterexample impossible to define homology of x with coefficient q with nice properties. This one cannot do. Namely, there is a counterexample which shows that one wouldn't be able to do it. Namely, consider E x equal E elliptic curve over field FQ of characteristic P. So suppose we can define cohomology of X with coefficients of some field. Now the idea is that this curve can have many endomorphisms. So the morphisms of endomorphism of curve, I mean that endomorphism of group curve. So you consider endomorphism maps 0 to 0, and it is automatically group endomorphism. So we consider end of E. And now over complex numbers, end of E is always commutative ring. Usually it is just C, sometimes it is quadratic extension of C. But over FQ, there are some curves which are called, how are they called?
Super singular.
Super singular. Yes, for which this thing is not commutative. Now, these things should act on these cohomologies. So that's the idea that any morphism will act. And now the claim is that you just know the structure of the thing. It is essentially some lattice in division algebra. And
End of
some division algebra over Q. And this division algebra, just over Q, for instance, it doesn't have two-dimensional presentations. You expect that your cohomologies will be two-dimensional.
But it might be trivial action.
No, it's not trivial because multiplication by n, for instance, is given by
Multiplication by 1 is given by 1.
yes, for example. Yes.
No, trivial action. So everything can make. So it's action. It's endomorphism group or endomorphism?
Group.
Endomorphism group. So it should be a representation of the group G.
No. What group G is? There's no group G.
End of E is a group, yes?
No.
It's a monoid.
It's not a group.
It's not a group. It is a ring.
It's ring. Why it's ring? Cannot add.
If you have any abelian group, it's endomorphisms with a ring. You can add.
And you should have a group or a ring morphism between N
Yes.
and E.
Yes.
This, and then you say that there are no unit of group.
Yes. So there's no such thing. So hence, you can define it. It's true. You can define if K is Q, cannot define. Now, if K is QL, where L is not equal to P, then can define.
And if
When K is equal to QP, cannot define.
And if K is Q but you're walking over characteristic 0, if K is Q and you're walking over characteristic 0,
Over characteristic 0, this endomorphism will be
so in general, over
commutative.
characteristic 0, there is a hope to define homology?
Yes, sure. Yes.
And beyond hope, it's
No. No. In characteristic 0, everything is
in
defined.
characteristic 0, there is a notion of homology coefficient in Q.
No. One more. There is notion. So, okay.
There is a hope.
It is. No. It's. Okay, we can discuss. It's more complicated because the question is, what does it mean? It's very, you see, when I said that it's impossible, think with nice properties. So it's a very subtle thing. So what does it mean? So what does it mean to define cohomologies? Cohomology is two-dimensional space. There are not too many two-dimensional spaces. What?
Functor from algebraic varieties to vector spaces.
So probably it's probably impossible. But
you don't have such a good explanation like here.
Yes. No, in this case, one can do it in a slightly more complicated situation if you want to compute not only cohomologies, but also, for instance, fundamental group. So then this example of algebraic variety over some field of characteristic zero for of some k, and two embeddings of k into complex numbers. They give you two algebraic varieties which have different fundamental group. Cohomologies are nature is the same because they have the same dimensions, so they're not naturally isomorphic, they're isomorphic. We don't know whether their nature is isomorphic or not.
The zero homologies are also isomorphic? The homologies coefficient, the cohomologies coefficient in Z are also isomorphic?
Yes.
This is a theorem, yes.
Okay. Probably it can be proven. Yes. Okay.
Can I ask a quick question?
Yes.
So I heard of something called crystalline cohomology, and I've heard that it should work for the case of QP in this instance. Is it just less nice in some way, or?
No, okay, it will be. So what I said that this space, I said that it can have two-dimensional representations. So maybe this cohomology will be not two-dimensional. Okay, so it will have different properties. That's the idea. Okay, so now I want to say that, in fact, Weil gave some construction in some cases, namely, but more or less in this case. Suppose he said that suppose that E is elliptic curve. So then, let's construct this cohomology in this case. Namely, we consider the following. Consider morphism E into E multiplication by n. Point x goes to nx. This is homomorphism of groups, and it's easy to show that the degree of this morphism is equal to n squared. So this means that if I consider the kernel of this morphism, this will be a finite group of size n squared. So the only problem is that it might be that it has n squared points, but some of them may be the same. So if n is prime to L, prime to P, then kernel of this n, let's denote this T n. No, T, okay, kernel n. Will have number of points will be n squared. And if it is not prime to P, then it's easy to show that number of points will be smaller. That this kernel will be, as a scheme, it will have dimension n squared, but number of points, actual points, will be different. Okay, now what he said, let's consider, let's define for if L is a prime different from P, define CL of E is equal limit, inverse limit, K P to the L. Signature mapped. So this is isomorphic to QL squared, it's two-dimensional, not QL, ZL squared.
I think we fixed P and you want to take probably powers of
P.
the
K P to the P, yes, K L to the I, L to the N, the limit over N. Okay, and then let's define, just by definition, by analogy with complex situation, H1 E with coefficients in QL equal morphisms from TL of E into QL. So in case of complex numbers, it will give you correct answer.
The kernel.
Kernel. Kernel of L to the n. So we consider groups kernel of L to the n. This is group which is isomorphic Z modular L to the n Z squared. And you consider projective system of these things and define it. Clearly, if you have morphism from E to E, it acts as this thing. Okay, so this was, so here we see why L equal P is not good for this construction. And for any other L, in this case, everything works. Okay, so now, so we have cohomology of X with coefficients QL. We cannot define this conjecture. So his conjecture was that we can define cohomology with coefficients QL. Okay, so now, yes.
Is it true that it doesn't matter what L you choose for the dimensions? It doesn't matter what L you choose?
Yes. Not only for dimensions. Okay, so let's consider further. Okay, so what we can tell here, and we have Frobenius X in this space. And we can consider eigenvalues of Frobenius. So eigenvalues of Frobenius lie in QL bar. So question, what does it mean? For example, that how to formulate second weights conjecture. Second weights conjecture makes sense only for complex numbers. And these are elements in QL bar. Okay, so, but here the claim is that these numbers, in fact, lie in algebraic integers. Claim. And this is general phenomenon, lambda I are algebraic. And the idea, for instance, in this case, is the following, that we have seen that number of points on, if you consider E of Q to the L for different L's. The number of points here will be integer all the time. And this integer is written as sum of powers of lambda. The claim is that this gives enough equation to show that lambdas in fact are algebraic numbers.
So what is EQL again? Just the number of points.
Number of points here. We know that it's equal to the, and here of course proved. In this case it's easy to prove that it's equal sum of, so plus minus lambda I to the power no, also this, it will be 1 plus q. So in this case it's 1 plus q plus lambda 1 to the A plus lambda 2 to the A minus. So since it's minus. And now for all L, this integer.
Probably q power L as well.
Yes.
This
Yeah.
was already proven by way?
Hmm?
This was proven by way, yes?
Yes. Oh, this is easy.
Ah, really?
No, you just compute. These are very explicit computations.
And where did it chaos in general?
Yes, very good. Hasse did this case.
Hmm?
Dorian Hasse already gave this case.
Yes. But this implies that lambda 1 and lambda 2 are in fact algebraic numbers. And moreover, this doesn't depend on, okay, L is not good. Let's write here N. And this also shows that this pair doesn't depend on, as algebraic numbers, this doesn't depend on L. Because this way, this huge system of equations.
How does it show that lambda I are algebraic?
Because they satisfy these equations for n equal 1, 2, 3. So it's too many equations. Okay, so next thing which we in fact proven is that lambda I is equal q to the 1/2. Absolute value, complex absolute value. In this case is equal to q to the 1/2. So this requires some study of elliptic curve, and okay, this was one, if you want, one of manifestations of this weight phenomenon. Okay, so this was weight conjectures. Now, we haven't talked about sheaves for trivial reason that at this moment sheaves were not invented. They maybe were invented, but they were not yet developed. It's notion of sheaves. So several people tried this very impressive conjectures, and several people tried to do this. Dwork did it. Some of this just to. So he related this to some L functions. They try to construct these L functions. So Grothendieck realized, so when he started to work, and he very soon realized that you cannot do geometry without sheaves, and so he realized that one should, in fact, prove more general thing, namely establish everything at the level of sheaves, not just homologies of some varieties. So that's what he started to do. Okay, so maybe let's make a break at this point. I think it's